Right, um, so you saw Randy do a bunch of work on this, the trash level app. We're going to continue that, talking about metrics. So we're going to start with some slides in the presentation to talk about C groups and namespaces, and then we'll have a little demo around kind of finding the sweet spot, right? So we've defined liveness probes and readiness probes, but one of the things that the scheduler obviously uses for placing the application is resource requests, right? A lot of times when I'm talking to people about understanding the scheduler in Kubernetes, I try and distill it down to kind of three categories, which is resources, right? Things like CPU and memory, string matching, right? So like things like affinities, anti-affinities, and then things like volumes, right? So the scheduler is going to take this stuff into account. So how do we tell the scheduler what our application needs, and then once it lands on a node, how do we tell the kubelet how to treat it once it sits in place, right? So the subtitle is finding a good flat and not getting kicked out, right? So if you've ever had an application that has been evicted, you know exactly what's going on here. So a little bit about me, by the way. I've been teaching quite a while. I'm a CKAD and a CKA, and some of my previous life was spent in application performance management. So I have done some APM for applications, and it was a lot easier those days because it was like instrument the code, and then it hands off to the database, and then goes back to the app tier, and everything was really easy, right? Nowadays it's like distributed tracing, and it becomes way more complicated. So I've also done a bunch of presentations. I did a presentation in Shanghai for Helm and some of the CNCF programs, and I'm actually going to be in Amsterdam the end of March to do zero downtime rollouts with controllers. So always fun to present. So I have a little talk here in 3 movements, which is essentially how resources are managed in Linux. So we'll have a little low-level discussion about what happens in Linux when our applications are deployed, getting killed versus getting evicted. So what happens with OEM versus the kubelet saying, hey, I'm out of resources, and I got to pick somebody to get rid of so I can save myself from peril, and then resources in harmony with Kubernetes by defining some of this stuff. So first, how resources are managed on Linux, right? So we've got, again, C groups in 5 minutes. So we've got several processes here, and they're running inside containers, and we want to be able to control how much resources or how much access they have to resources, right? So nice little diagram there of some processes and allocations for those processes on a particular host, right? So I'm going to borrow this from Randy because I heard it once. He said, everybody here seen The Matrix, right? Anybody not seen The Matrix? You're missing out. You should go see it. But if you have seen The Matrix, there's a point where Neo goes into the Oracle, and he's sitting in the lobby waiting to see her, and he says, he's looking at this kid, and this kid's bending this spoon all over the place, right? And he goes, what's the trick? Anybody remember what the kid says? There is no spoon, right? There are no containers, right? Every Linux process is essentially containerized. Right? A lot of monitoring tools will call processes in the that are not containerized in the root container, right? So there are no pods, there are no containers. This is all, I like to say, a way of selling software with a cute little whale mascot, right? for containers, right? However, there are C groups and namespaces. This is what's important because we want to be able to tell Kubernetes about these things, right? So processes as a unit of isolation is where we're at with modern applications, right? So we define these system resources amongst a group of processes, and essentially that's our program, right? So we've got a series of instructions. In our case, with our demo application, it's not very complex, but obviously in reality we have very complex things happening to provide functionality through a microservice. And so these processes on our Linux hosts have the private virtual address space and a nice factor for allocating their access to the CPU. Right, so what we want to do, oops, I went the wrong direction. Now, if we don't have containers, right, one of the problems with traditional process controls, right, is because we want to have access, the process wants to have access to memory and CPU, that one of those processes could be a bad neighbor, right? Could be building a barn in their backyard and keeping you up at night, or whatever it might be, right? So we don't want noisy neighbors. We want neighbors who are nice to us and don't have their dog barking all the time, right? So any process without containers can just allocate what they need on the system. And so the highest priority process then gets the lion's share of its resources, and then starves other processes, right? And so we want to make our applications all be nice neighbors to each other, right? And so the way to do that is through C groups and namespaces, right? So we want to efficiently share the host. We've got to have this flexibility not to have this overlapping use of resources. And this goes not just for applications, but there are tons of settings even at the Kubernetes level. So applications are going to have C groups. They're going to be assigned to, from a platform level, even the processes running on the platform like the kubelet, like Docker. We want to have them have their own C group hierarchies, even required system level processes. When we talk about running a platform, those need to have their own hierarchies so that we don't have them contending with one another. So the C group mental model here, right? So we've got the threads running in containers, or in one case we've got in container A, we've got a couple threads running in a process. We also have a single threaded process that is running. Both of those models are okay. And so they're going to have their own resources and threads, and we're going to have those control groups that allow us to say, this is how much resources you get, and we're either going to throttle you or we're going to prevent you from consuming any more, right? So two different models here where we've got container A with a single threaded process and a multi-threaded process, and then container B that has multi-threaded processes. And so multiple control groups can then control a single process, right? And so the most controlling group is the limiting factor, right? This is a hierarchy. So for example, if you're running a container under Docker and you don't use a C group flag like CPU share, or memory, then their constraints are inherited by the parent, right? Docker has the sum total, typically, of the entirety of the resources on the node as its disposal, right? So if we do use something like CPU share or memory flag with Docker, then that takes precedence, right? So the container only has some subset of resources that it can use, right? So the number of resource controllers, not all of these are obviously available through a containerizer, but it turns out the most important ones tend to be, right? So things like memory, CPU, and I/O are all available to us through our containerized systems. You can see here on this slide that we've got the newer versions of C group, or C group version 2, right? So I/O replaces block I/O. Perf event is the same as perf event on the version 1, but you can see the Linux kernel version that you need for each one of these newer C groups. So you have some equivalents, you got some renames, but your containerizer right now likely is backwards compatible to an older kernel and therefore isn't using C group version 2 yet, but eventually we'll get there, right? So to kind of reduce the cognitive load, we're talking about C group version 2 here, but right now we're still using version 1. In any case, what we're still trying to do is obviously control the primary resources that a process needs, CPU, memory, those types of things. Okay, so now getting killed versus getting evicted, right? We've got an operating system level operation that will take a process and kill it if it runs afoul of some constraint, or we've got a node level agent that is also going to take action if a process violates its constraint, right? So two different things here that we're talking about. So the OOM killer, right? When we run out of memory on our nodes, right? When all else fails, we want to kill a process, and we want to kill a process that is going to prevent this condition from happening again. So we're going to kill a process not necessarily that has caused the condition, but rather one that may be consuming the most of a resource. In other words, it may be not the one that you expect, right? So we can immunize certain processes against the killer, right? So for example, if you run your Kubernetes cluster as containers, we can rank the order by which we kill processes. And so that way, the node level agents, the control plane agents, they're all going to be the last thing that gets killed, right? This is still just a suggestion, not necessarily a kind of a hard fact, but it does let us control things to some degree. And so we, essentially what we use is the Badness algorithm, right, in order to do this. And so you can kind of see 1, 2, 3, 4, 5 are the steps that we take, right? So we lose the minimum amount of work done, right? So again, it may not be the process that you expect to get killed because we want to lose the minimum amount of work, but we also want to recover a large amount of memory, right? So being able to recoup more memory when it comes to badness means that we will avoid evaluating badness again more likely if we recover a large amount of memory, right? We don't want to kill anything innocent of eating tons of memory. We don't want to kill the minimum amount of processes, right? We want to kill the process the user expects to kill. So it does try to kind of understand that we have an expectation, humans have an expectation, but again, it is an algorithm that's going to provide the OOM kill, right? So when the kill happens when one of our processes is going to get selected for shutdown by the system when it's low on memory, and it's not necessarily the one that just caused that condition, right? It's going to be something that also meets the conditions of that algorithm. And this can also occur when, obviously, our process tries to exceed its C group limit, right? There are all sorts of things that can cause this condition, but typically OOM or can cause a process to die or get killed, but OOM is obviously one of the most common things, right? So if our container's PID1 process dies, then the local kubelet will restart it, right? So whatever process gets chosen, let's say we don't have any necessarily any ranking for any of the processes, we just had kind of everything as best effort, then the kubelet's going to restart the thing that got killed by the operating system. And then should the entire node go down, we've got a second layer of reconciliation that when it comes to Kubernetes that we can reschedule, right? We've got this control loop in place that detects that we desired 3 replicas and there are only 2, and we're going to reschedule that somewhere else on a surviving node. However, on the node itself, we've got the node agents kubelets that are responsible for protecting themselves, right? The kubelet has to have some amount of resources for itself, and typically one of the recommendations of the Kubernetes maintainers is enforcing node allocatable, right? So node allocatable allows us to reserve a little bit of resources for the kubelet, but at some point, if we're being efficient about the use of resources on our nodes, we're oversubscribing them to some degree, right? Because we have different categories of resource requests and limits that are happening with pods. And that comes down to the first bullet here, which is QoS, right? If I've got best effort pods, if I've got burstable pods, if I've got guaranteed pods, and I'm probably going to have some mix of those things, then I'm oversubscribing a node. I'm being efficient about essentially the ROI of my infrastructure, right? That If everything was a guaranteed pod, most of my nodes would just sit there idle, and I'd be essentially overpaying for resources, especially in the public cloud. So I don't want to do that. I do want to oversubscribe, but that also means that the kubelet needs to take into consideration which pods it needs to be able to kill when it comes to QoS. And that all comes down to resource requests and limits. But again, how do we set that at the application level? So that's what we're going to do, is look at the ability to detect what is the optimal settings for those, and when we should be also killing an application, because it may continue, for example, in the example that we're going to show, continue to allocate memory and provide no value, right? So we'll set those levels, and that'll give us a QoS. Pod priorities. So this allows us to say, well, this particular set of processes should have priority of some other less mission critical application. Pod disruption budget, so we can say, well, I would normally choose this particular process, but because it's already at its minimum number of replicas, we don't want to choose that one. And then things like soft and hard memory thresholds. I've had folks that I've worked with before say, and this is sort of the, it sort of happens on a node level where I've got these applications that I've deployed, and the most important of which tends to use the most resources. But if I haven't set something like quality of service levels, obviously the kubelet, using its node hard and soft memory thresholds and its minimum reclaim, is going to say, well, this particular process is using the most resources. I want to avoid a pressure condition as long as I can. I'm going to choose that one. Well, the applications that tend to use the most resources tend to be the most important ones. So I've had folks that I've worked with say, why does my database keep getting evicted from one node to another, right? Because they weren't setting the information inside the deployment manifest for resources to give it the proper QoS, right? So we're operating on several different levels here. So resources in harmony. Ideally what we've got is some sort of resource request, some sort of resource limit, but the question still remains, how do we get there, right? How do I know that app v 2.2 needs 128 megs of memory and a quarter of a core of CPU, and that its limit should be 256 megs and half a core of CPU? I have to somehow profile that application to tell me that's the sweet spot when it comes to the best operating window for that application. This is where the magic happens, right? Actual command line utilities and GUIs is where the magic's going to happen. So first off, what I want to do is show a couple things. Number one is I'm deploying something on Kubernetes, right? So just for complete transparency, what I want to do is show you just the manifest, right? So I've set up a service, and this service has a static cluster IP that I can then connect to the application, right? This is the code that Randy was showing you before with the added metrics endpoint, right? So I don't want to have to worry about pod IPs, right? Try and find them. I'm just going to use this static cluster IP. Now inside the deployment, I've got a single replica, which I can then scale if I feel like that's required. We've got the trash levels. We've got an app component, which is going to be obviously the trash levels code that Randy was showing you. And I'm using the classic Prometheus.io scrape for the metrics. And so there's our trash levels code. I'm just pulling it off Docker Hub, right? So now I've also got a client that I want to hit this code with, and I don't want to do that manually because, well, using a host terminal is not usually the way that we hit services with, right? We use another container. And so this deployment, again, just replicas one. If I want to put more pressure on the application, I can scale it up. And this is just a Ubuntu container that I've basically put this for loop. Now I'm using that static cluster IP and just hitting the CANs endpoint. There are several CANs endpoints to that code, but I'm just hitting one of them because of what I want to do is get performance information, right? So I've got several different manifests inside this manifest directory that I'll show, all right? So there's my my manifest. So what I'm going to do is just kubectl apply the. Oh man, typing with one hand is not easy, right? Here's the other problem with this is there's a beer here, and I've got a microphone, and I don't have 3 hands, right? I need access to a keyboard, a beer, and a microphone. No, you're. Yeah, exactly. Thank you. Okay, so what I'm going to do is just kubectl apply the trash app, right? And Ron, thank you so much. So I'm just going to let this warm up for a second, right? I'm going to set a timer to let this guy warm up because what I want to do is show like the response time that'll happen immediately when I start the thing up. But I want to give it a moment here to warm up. And then what we're going to do is it has an endpoint where it's going to allow me to allocate more memory, and we're going to see the performance difference when we allocate more memory and see that curve happen. But what I want to do is give it some time to kind of warm up and give Prometheus a moment to catch up. So my Prometheus scrape is about 10 seconds. So every 10 seconds I'm getting a Prometheus scrape. Obviously we don't do that normally with production applications. We're gonna put a lot of load on it, but what I want to do is get a lot of metrics really quickly. And so I'm going to scrape it every 10 seconds. So now that it's been running for nearly a minute, I'm going to run my client. Right? So we saw that the client has a loop that's going to run 1,000 times. It's just going to hit that cans endpoint. Right? So now I can run this guy. I've got a minute in. And so I've got my trash client. Right? So if I do a git, here, hand that for a second. If I do wow. I know, exactly, right? I don't have an excuse. Right, so that's really small because I'm trying to keep all the real estate for the Prometheus. You can see I've got my cluster IP, I've got my trash app, and my trash client, right? And so now what I'm going to do is every minute, whoops, I got to do a. I'm going to do this, hit this metrics endpoint. Oh, sorry. You know what? Hang on, let me cancel that. So what I need to do is hit the endpoint for scaling, which is the memory. There we go. Sorry. So I'm essentially going to allocate more memory. Right? So now I've got this message that I've got memory allocated for the application. So let me go back up to these PromQLs, right? I've got the rate of the hello call counter. So that's just going to count how many calls the thing is receiving. And so I've got this kind of per second amount of calls. And so you can kind of see that sort of hanging off the page here. Let me see if I can get it. There we go. So right away, from 0, I've got a lot of calls that are happening. Now I've got the average time that a call will take, taking the sum divided by the count, right? And so I've got, notice when the application first started that it's taking essentially 11 seconds, is obviously artificial, to respond, and now we've got a dramatic drop off because I've allocated more memory for the service, right? Now that I've given the application more memory, or let's say it was self-allocating memory, it's speeding up, right? And I can see here that I've got the mem gauge, right? And so I went from 0 essentially to 8 megabytes of memory. And let's see if I can reclaim some of that real estate. There we go. Now let's do it again. We're going to allocate more memory, right? So the application starts to warm up, it's allocating more memory, and it's going to speed up, right? This is our expectation around the application gaining some performance as it starts to allocate memory, right? So now I've got, again, my three graphs here. Let me pull some of this over so that we can get the whole graph, right? We'll execute this guy again, and I'm still at this steep climb, right? What I would expect. I'm getting more performance out of my application, and I'm spending less time in the response, right? I went from 11 seconds, now I'm under 6, and I've got more memory that's being allocated, right? So my expectation again is that adding more memory to the application, it can handle more requests, right? So let's do that again. We're going to allocate some more memory for the application, give Prometheus a moment to catch up so that it reflects the new memory. There's our new allocation for memory. So I'm stepping through the allocations of memory, and I should see the performance continue to improve for the application, right? I still got this steep climb, right? I'm still building up to the peak performance of my application, and also reducing the amount of time that each one of oh, wait a minute, what just happened here? I'm not getting as much efficiency as I would expect, right? Because the graph is showing me that there's a little bit of fall off, right? You can see that curve over time is showing me that I'm not getting as much performance from the memory that I'm allocating, despite the fact that I'm still able to respond to more requests per second, right? So let's continue that trend and see about allocating some more memory for the application. And based on that current trend that I see here, I'm a little bit worried that I might see some more fall off in performance, but let's make sure that Prometheus sees our new allocation of memory. There it is, right? We've got our steps, 1, 2, 3, 4, 5 going up. And now we've got, a little bit more fall off, right? So the application is not becoming as efficient with the additional memory that it's allocating. And I'm still in a pretty good spot, right? Or I've got some good performance. My response time is really low, and I'm getting more and more requests per second, right? I'm still kind of on this steep climb. Although again, on my requests, how many calls I'm getting, you can see a little bit of fall off happening at the end here, right? So we'll kind of continue this trend. So I can really start to predict kind of a sweet spot happening here, right? Where I know that with a certain amount of memory based on this graph that I can predict that I'm getting close to about peak performance for this one replica of my application. So let's go again and allocate some more memory for the app and see how it responds. So this is all about profiling, right? I have no idea what the performance of the application is going to be until I start to really understand how it's going to respond to these requests from my client. Now I've got even more fall off when it comes to performance, right? I've allocated more memory, but I've not been given the performance that I would expect, right? In here, I got a massive amount of fall off for that tiny amount of memory, but now I've got just a little bit more performance gain, right? So I'm still okay, but I'm starting to see kind of the top threshold of the application at this point, where I might want to think about, okay, maybe scaling the application, maybe limiting it in the amount of resources that it's going to consume. And again, at a certain point, we're going to see that it will completely fall off, right? So let's try and scale again. Let me bring up the counter, right, so we know where we are and how much time. Going back to our graph, making sure that Prometheus keeps up with what we're doing. We've got another step of allocation of memory. And what are we at? 50 megs, right, of memory. So again, this is a contrived example, but shows us a really clear pattern of performance around the application. Right, so now I've got to the point where I still got a lot of requests from my application. I'm still not at the point where the client is too slow for the application, right? The application can still handle all the requests that are coming in from the client, but I'm starting to fall off on the capability. And now we start to see this level off, right? Where I've got an optimal amount of time that I'm responding. Remember, we're starting from 11 to show this kind of artificial high number for us humans, right? The expectation in reality, this would be some tiny amount, right? We want to be able to respond really quickly. But in this case, we're artificially showing this trend. So let's try one more and see if we get anything out of it. And let me move this back over here so it's not blocking. There we go. Now, Prometheus shows us we've allocated a little bit more memory. There we go. Now it's caught up a little bit. Got a little bit of a lag for Prometheus metrics. And we'll execute one more time. And I don't really see any more benefit, right? I could continue to allocate more memory, but I'm not going to see any more performance from this. So at this point, it's essentially a waste, right? And so although my requests per second are getting close to essentially up to the peak here, I'm probably past the point of really getting value out of this application at this point, right? So I'll let this run a little bit more and allocate some more memory and see how it does. But I think we've kind of got that sweet spot where we've got an indication of where we're at, right? So we'll do one more time and see how that affects things. But I think we're pretty close to where we would want to cap this thing out, because any more memory that we're allocating is just going to be wasteful and not going to give me the performance that I would expect, right? So I'm essentially flat here, and I got a few more requests, but really not that much, right? I'm trending off. So this gives me a really informed position, right? I know where the sweet spot of the application is going to be. So this really gives me ammunition to tell Kubernetes, okay, I know that my application optimally uses this amount of memory, and I know that above this amount of memory, essentially I'm just wasting resources that could otherwise be used for an application that could use those resources and not wasting them on my nodes, right? And minimizing ROI, essentially. So we'll do this one more time, right? We're pretty close to being topped out here, and we can't gain any more time. We can't get anything faster, right? Even though we add more memory. So I'll do this one more time, let it run in the background. But in reality, what that means is we've got kind of a sweet spot. And what that does is inform where, notice in this first deployment, I don't have a resource request or a limit, because I don't know what the application should be using, and I don't know where I should kind of prevent it from continuing to allocate memory. So now I have kind of an informed position, right? So going back to Firefox, right where I've got this kind of top end, I can say, well, we probably don't want the application consuming more than this, because it's really not going to give us any value, right? So that's my assumption I can make. Okay, don't let us get up here, which correlates to how much memory we're consuming here, right? And I've essentially topped out on the request that the application can manage, right? So now I can go back to my Kubernetes specification and say, well, I know that my sweet spot, so let's just go down to, so here's my promql just for, again, for completeness, right? We've got a rate of how many calls we were doing, the average amount of time each call would take, and then how much memory, right, just for completeness. And now if I re-evaluate my deployment for my application, I can inject my requests and my limits, right? So I know that the application is just going to be wasteful above 70 megabytes of memory, right? I can say that pretty much with 99% certainty, that anything above 70 megs of memory, this application is just going to waste, right? If I continue to allow it to allocate memory, it's just not going to give me anything. And this sweet spot is about 24 megs of memory. So I want to make sure, remember that the request the scheduler is using to determine where to place the application. It's not about the low-level kernel configurations. That's what the limit is for. But the request is what the scheduler is going to find a node that says, hey, I've got at least this amount of memory free. Let's put this application there so that it has a good home. And we don't run into things like evictions, right, where the kubelet's not going to be hostile toward the application. So now I have a really good informed position to say, this is my sweet spot, right, for my application. Now I'll do you one better even. I also have an informed position to take when it comes to auto-scaling, right? If you guys are familiar with the horizontal pod autoscaler, well, how do I know what that threshold should be, right? I have an informed decision here, right? I can say for my resource metrics HPA that, you know, my average value may be 50 megabytes. I should probably add another replica of my application so that I never reach that kind of top level, right? What I don't want to do is necessarily kill my application. I want it to allocate enough memory to respond to my clients, but I don't want to kill it. So I'm going to add more replicas to it. On top of that, I also have an informed decision around requests, right? I know how many requests are going to happen before the thing tops out. So now I can also add to that, if I'm using the Prometheus metrics adapters, my kind of call per second metric, right? I can ingest that PromQL and say, when I get to about 0.8 M, which is what we saw right below 1.0 in our graph, then I can scale on that too, right? So I can have an OR condition that says, when I reach that many requests, when I reach that amount of memory, I should probably add more replicas to my application. I avoid getting killed, and I keep the application healthy through liveness and readiness probes, making sure that it's always responding to requests or isn't responding to requests when it shouldn't. And then also making sure that I have enough replicas based on how many requests are coming in. Okay, so they're taking the hooked cane thing and pulling me off of the stage. So I think that's all we've got. But thank you guys. I appreciate all your time and attention. And so this is our kind of rough graph. Thank you so much. This is kind of our rough graph of diminishing returns, right? Making sure that you scale at the right point and you give the application the right resource request and limit. All right, folks. Thank you so much. I appreciate your time, and thanks for coming to the meetup.